Hello everyone, welcome to this session on Introduction to Time Series. Today in this session, we'll be taking you through various concepts that are involved in creating a time series model. So let's go ahead and see what all we'll be covering in this session. So first off, we'll start off with understanding what is time series and then move on to discuss the different types of time series out there. After that, we'll be discussing the various components of time series and then move on to discuss how we can fit the model of time series using three methods, which are differencing and then Decomposition and finally the ACF plot method. Once we're done with that, we'll move on and understand what is the ARIMA model and then move on to discuss how we can create a time series model using the ARIMA method, and then we'll be done with the session. Alright, so before we begin the session, guys, if you haven't already, please subscribe to the Intellipaat channel and also comment down any queries that you have in the comment section, and we'll be happy to answer all your queries.
So let's start with time series forecasting. Well, to put it simply, time series forecasting is the use of statistical models to predict future values based on past results. So what kind of variables can we forecast? So any value that can be tracked and collected over time. Think of annual population data or a company's daily stock price or quarterly sales figures. For each of these examples, data is collected over time and the time series model simply uses that data to forecast future values. Now we'll concentrate on some of the building blocks of time series model. The first defining characteristic of a time series is a list of observations where the ordering matters. So ordering is very important because there is a dependency on time, and changing the order could change the meaning of the data. Now to accurately forecast future values, we'll need each measurement of data to be taken across sequential and equal intervals, and with each time unit having at most one data point. So once we have collected our data, we have two objectives in mind. So first would be identifying the patterns represented by the sequence of observations, and second would be forecasting or predicting future values of time series. So the patterns we observe will tell us a story of how a business interacts with time. In time series analysis, it is assumed that the data consists of a systematic pattern, that is usually a set of identifiable components, and random noise, that is error, which usually makes the pattern difficult to identify. So most time series analysis techniques involve some form of filtering out the noise in order to make the pattern more notable. So now we'll learn about the different types of time series models. So the time series data could either be stationary or non-stationary. So given a series of data points, if the mean and variance of all the data points remains constant with time, then we'll call that series as stationary series. So here on the screen we have a simple example of how a stationary series will look like. Now it is important to know about stationary model because of the fact that without a stationary series we cannot move forward with time series analysis, and we would have to need to calculate the mean of a time series in order to estimate the expected value. But if the time series is not stationary, then our calculation for expected value will give false results and interpretation. So now if a series is not stationary, then we'll need to convert the non-stationary series into a stationary series. In order to do this, we'll have to differentiate the series. So apart from a stationary series, a white noise series is a series where the mean and variance of the data points is constant, but there is no autocorrelation between values of those points. So the correlation between values of data points at different time intervals is known as autocorrelation. It is also sometimes termed as lagged correlation. Now when the mean and variance of time series data is not constant, that is varying with time, then we can say that the data is just taking a random walk with time. So random walk is a term used when data points in the series are not dependent on their past values. This makes the series non-stationary series because the mean and variance will vary with time. So there are three basic criteria for a series to be classified as a stationary series. The mean of the series should not be a function of time. Rather, it should be a constant. So here the green colored graph satisfies the condition, whereas the graph in red has a time dependent mean. Then the variance of the series should also not be a function of time. This property is known as homoscedasticity. So over here you can notice the varying spread of distribution in the right hand graph. And the third criteria is the covariance of the ith term, and the I plus mth term should not be a function of time. In the graph here you will notice the spread becomes closer as the time increases. Hence, the covariance is not constant with time for the red series. So next we'll study about different components in a time series data. Now, as we know that a time series data varies with time, there are many factors which results in this variation. The effects of these factors are studied by the following four major components: trends, seasonal variation, cyclic variation, and irregular variation. To better understand and apply these models, we'll examine a business problem surrounding how management at Hotel ABC, a mountain resort, is able to prepare for their year by forecasting the number of room bookings they expect each month. So, this information can help management make informed decisions on staffing, hospitality arrangements, and pricing for rooms. So, they have tasked their business analysts to forecast bookings so they can make the necessary preparations. So the historical data contains monthly information from the past 10 years, and the forecast should contain monthly bookings for the next 6 months. So your job will be to use the historical bookings data from the past years to investigate and clean the data and then determine the trend and seasonal components. After which you'd have to apply the findings to an ARIMA model and finally forecast the bookings for the next 6 months. So that's quite a lot to think about. But don't worry, we'll be taking a closer look at the time series forecasting methods and what they all mean. So before we crunch any numbers and make a predictive model, we need to plot our data in order to get a feel for what a time series looks like. And time series plot shows a graphical presentation of the relationship between time and the time series target variable. So time is on the horizontal axis and the target variable's values are shown on the vertical axis. The first plot shows the complete ABC hotel time series. So you can see that the series shows a general trend up, and we call that an upward trend. Lastly, our bookings plot shows two main patterns. First, we see the upward trend. Secondly, we see some regularly occurring fluctuations up and down within the same calendar year. So we call that a seasonal pattern. So plotting out the time series allows us to visualize these patterns and behaviors. We can then use our findings in the time series plot to create and fine-tune sophisticated forecasting models. In our time series analysis, a trend is a gradual shift or movement to relatively higher or lower values over a long period of time. So when a trend pattern exhibits a general direction, which is upward, where there are higher highs and lower lows, we call this an uptrend. And when a trend pattern exhibits a general direction, which is down, where there are lower highs and lower lows, we call this a downtrend. So a time series can experience changing direction where it can go from an uptrend to a downtrend. And if there were no trend, we call it a horizontal or stationary trend. So each trend we see in a time series is called the trend cycle. When looking at the plot of the bookings data from ABC Hotel, we see that ABC Hotel continues to increase their bookings year on year, creating an upward trend in the time series. So if ABC Hotel reaches capacity, then bookings will trend sideways. And should a competing hotel open up down the street and steal their bookings, then ABC would experience a downtrend. So a time series that exhibits a repeating pattern at fixed intervals of time within a 1 year period is said to have a seasonal pattern or seasonality. So seasonality is a common pattern seen across many different kinds of time series. For example, if you live in a climate with cold winters and warm summers, your home's air conditioning costs probably rise in the summer and fall in the winter. And you would reasonably expect the seasonality of your air conditioning costs to recur every year. Likewise, a company that sells heavy coats would see sales jump in the winter but drop in the summer. So companies that understand the seasonal patterns of the business can time inventory, staffing, and other decisions that coincide with the expected change in business. So what we see now is a seasonality plot. Again, in all time series plots, the vertical axis is our target variable and the horizontal axis shows our seasonality. For example, with monthly data, all the monthly values are plotted in chronological order with each month on the horizontal axis. And the numbers 1 through 10 represent the 10 years of data that we have seen in the time series. And when looking at this plot with the ABC Hotel time series, we can tell that our results during winter and summer months are significantly higher. So these findings are not surprising, considering most people go to the hotel during these months to take advantage of the skiing and hiking. Since this pattern repeats each year at the same time intervals, we can safely say that our time series contains seasonality. Another noticeable characteristic of the ABC hotel booking seasonality plot is that the magnitude of bookings increase year after year. So guys, keep this in mind as it will be very important for our predictive modeling. So one question which arises here is, what if we see a pattern in our data that doesn't occur within the same calendar year? Is that still a seasonal pattern? No, we call it as a cyclical pattern. So a cyclical pattern exists when data exhibits rise and falls that are not of a fixed period. So think of business cycles which usually last several years, but where the length of the current cycle is unknown beforehand. In finance, times of expansion and recession in the stock market reveal cyclical patterns. A cyclical uptrend is referred to as a bull market, while a cyclical downtrend is referred to as a bear market. And these patterns in the general market occupy multiple years and don't have a repeating pattern within each year. So many people confuse cyclical behavior with seasonal behavior, but they're quite different. So the fluctuations are not of a fixed period, then they are cyclical. If the period is unchanging and associated with some aspect of the calendar, then the pattern is seasonal. In general, with cyclical patterns, the average length of cycles is longer than the length of the seasonal pattern, and the magnitude of the cycles tends to change more than the magnitude of seasonal patterns. Also, cyclical patterns are much harder to predict as well. For example, the decline in stock markets is often too sudden and violent, all coming as a surprise to most. And the variation of observation in a time series which is unusual or unexpected is known as irregular variation. It is also termed as a random variation and is usually unpredictable. The example of irregular variation can be the time of strikes or natural disasters which are unusual or unexpected. So now that we've covered some of the basic building blocks of time series analysis, next we can start discussing the first model type, which is exponential smoothing model. So exponential smoothing forecasts use weighted averages of past observations, giving more weight to the most recent observation with weights gradually getting smaller as the observation gets older. So the E, T and S terms represent how the error, trend and seasonality are applied in the smoothing method calculation. So each term can be applied either additively, multiplicatively or in some cases be left out of the model altogether. This framework allows for a wide spectrum of time series analysis due to simplicity of the calculation. So how do we determine how to apply the error, trend and seasonality terms of an ETS model? A good way to start is to visualize the data by using a time series decomposition plot. So what this plot does is separate the time series into its seasonal, trend and error components. So let's start by looking at the data from a business problem. The first plot shows the actual time series. The seasonal portion shows us that there is a seasonal pattern. Our trend line indicates the general course or tendency of the time series. So it is a centered moving average of the time series and fits between the seasonal peaks and valleys. This line is considered deseasonalized. And lastly, the remainder is the error in the model that calculates the difference between the observed value and the trend line estimate. So it's the piece that's not accounted for by combining the seasonal piece and the trend piece. All time series will have this residual error to help explain what trend and seasonality cannot. And making use of the trend, seasonal and error plots shown together in a decomposition plot allows us to identify these main components of the time series. So later we can extract these components so that we can figure our exponential smoothing model to best represent the underlying data of a time series. So why do we need ARIMA model? So an ARIMA model is a class of statistical models for analyzing and forecasting time series data. It is an acronym which stands for Autoregressive Integrated Moving Average. So it is a generalization of the simpler autoregressive moving average and adds the notion of integration. So these ARIMA models are applied in some cases where data shows evidence of non-stationarity and an initial differencing step can be applied one or more times to eliminate this non-stationarity. So a random variable which is time series is said to be stationary if its statistical properties are all constant over time. So a stationary series has no trend. That is, its variations around its mean have a constant amplitude and it wiggles in a consistent fashion. That is, its short-term random time patterns always look the same in a statistical sense. The latter condition means that its autocorrelations which is nothing but correlations with its own prior deviations from the mean, remain constant over time, or equivalently, that its power spectrum remains constant over time. So a random variable of this form can be viewed as a combination of signal and noise, and the signal could be a pattern of fast or slow mean reversion, or sinusoidal oscillation, and it could also have a seasonal component. So an ARIMA model can be viewed as a filter that tries to separate the signal from the noise, and the signal is then extrapolated into the future to obtain forecasts. So what exactly is ARIMA model? The ARIMA forecasting equation for a stationary time series is linear. That is, regression type equation in which the predictors consist of lags of the dependent variable or lags of the forecast errors. That is, predicted value of y is equal to a constant or a weighted sum of one or more recent values of y or a weighted sum of one or more recent values of the errors. So the acronym ARIMA is descriptive, capturing the key aspects of the model itself. So AR means auto regression. So model that uses the dependent relationship between an observation and some number of lagged observations. And I stands for integrated. So this is used for differencing of raw observations. That is, subtracting one observation from another observation in the previous time step in order to make the time series stationary. And MA stands for moving average. So it is a model that uses the dependency between an observation and residual errors from a moving average model applied to lagged observations. And each of these components are explicitly specified in the model as a parameter. And there's a standard notation used for these three aspects, P, D, and Q, where the parameters are substituted with integer values to quickly indicate the specific ARIMA model being used. So P denotes the number of lag observations included in the model, and it is also called the lag order. D stands for the number of times that the raw observations are differenced, and it is also called the degree of differencing. And Q denotes the size of the moving average window. It is also called the order of moving average. So now we'll look at the assumptions of ARIMA model. So here the first assumption is that the series is stationary. Essentially, this means that the series is normally distributed and the mean and variance are constant over a long time period. Next is uncorrelated random error. So we assume that the error term is randomly distributed and the mean and variance are constant over a time period. So the Durbin-Watson test is the standard test for correlated errors. We also assume that there are no outliers in the series, as outliers may affect conclusions strongly and can be misleading. The last assumption is the random shocks or the random error component. So if any shocks are present, they are assumed to be randomly distributed with a mean of 0 and a constant variance. Now we'll look at the steps to build ARIMA model. Sometimes ARIMA model is also known as Box-Jenkins method. So the Box-Jenkins method is a stochastic model building process, and it is an iterative approach that consists of the following three steps. So the first step is identification. Here we use the data and all related information to help select a subclass of the model that may best summarize the data. And next step is estimation. So here we use the data to train the parameters of the model. And the third step is diagnostic checking. So here we evaluate the fitted model in the context of the available data and check for areas where the model may be improved. And this entire process is iterative. So as new information is gained during diagnostics, we can circle back to step 1 and incorporate that new information back into new model classes. So let's take a look at these steps in more detail. So the identification step can be further broken down. So first, we assess whether the time series is stationary, and if it is not, we determine how many differences are required to make it stationary. And after that, we identify the parameters of an ARIMA model for the data. Now let's have a look at some of the tips during identification. So it is advised to use unit root statistical tests on the time series to determine whether or not it is stationary. And also we need to avoid over differencing as much as possible. So differencing the time series more than what is required can result in the addition of extra serial correlation and additional complexity. Now we'll look at the steps for configuring AR and MA. So two diagnostic plots can be used to choose the P and Q parameters for the ARIMA model. They are autocorrelation function and partial autocorrelation function. So the ACF plot summarizes the correlation of an observation with lag values. The x-axis shows the lag and the y-axis shows the correlation coefficient between -1 and 1 for negative and positive correlation. While the PACF plot summarizes the correlations for an observation with lag values which are not accounted for by prior lagged observations. So both these plots are drawn as bar charts showing the 95% and 99% confidence intervals as horizontal lines. So the bars that cross these confidence intervals are therefore more significant and worth noting. Now you may observe some useful patterns when you make these two plots, such as the model is AR if the ACF trails off after a lag and has a hard cutoff in the PACF after a lag. So this lag is taken as the value for P. And the model is MA if the PACF trails off after a lag and has a hard cutoff in the ACF after the lag. And this lag value is taken as the value for Q. And the model is a mix of AR and MA if both the ACF and PACF trail off. So that was the process involved in identification, and the next step is estimation. So estimation involves using numerical methods to minimize a loss or error term. The method of least squares can be used for this. However, for models involving an MA component, there is no simple formula that can be applied to obtain the estimates. And the third step is diagnostic checking. So the idea of diagnostic checking is to look for evidence that the model is not a good fit for the data. The two useful areas to investigate diagnostics are overfitting and residual errors. So what do we do in overfitting? We start off by checking if the model overfits the data. Generally, this means that the model is more complex than it needs to be and captures random noise in the training data. So this is a problem for time series forecasting because it negatively impacts the ability of the model to generalize, resulting in poor forecast performance on data which is out of the sample data. So careful attention must be paid to both in-sample and out-of-sample performance, and this requires the careful design of a robust test harness for evaluating models. And what do we do in case of residual errors? So these forecast residuals provide a great opportunity for diagnostics. A review of the distribution of errors helps in removing out the bias in the model. So the errors from an ideal model would resemble white noise, which is a Gaussian distribution with a mean of 0 and a symmetrical variance. And for this purpose, you may use density plots, histograms, and QQ plots that compare the distribution of errors to the expected distribution. So a non-Gaussian distribution may suggest an opportunity for data pre-processing. And a skew in the distribution or a non-zero mean may suggest a bias in forecasts that may be correct. Additionally, an ideal model would leave no temporal structure in the time series of forecast residuals. So these can be checked by creating ACF and PACF plots of the residual error time series. And the presence of serial correlation in the residual errors suggests further opportunity for using this information in the model. So we'll be implementing all of these on top of the air passengers dataset. So let's quickly go to our studio and start working. Right guys, so this is our studio, and our first task would be to have a glance at the air passengers dataset. So I'll type in air passengers, and this is our time series data. So this time series data starts from the year 1949 and goes on till the year 1960. And all of these are just entries which tell us about the number of passengers for each month. So if we have a look at this entry, then there were 302 passengers during July 1954. Similarly, if we take this entry over here, there were 178 passengers during March of 1951. And if we take this entry, there were 405 passengers during December of 1959. And just to be sure, let's also have a glance at the class of this dataset. So it'll be class of air passengers. So we get TS. So TS is nothing but time series. Now let's also explore some time series functions. So the start function would give us the first entry point of the time series dataset. So start of air passengers, and this is the first entry point. So 1949, 1. So this basically is telling us that the first entry point is the first month of the year 1949. And similarly, we can use the end function to get the last entry point, which would be end of air passengers. The last entry point is the 12th month of the year 1960. right? So the first entry point is January 1949 and the last entry point is December 1960. Okay. Now let's also have a glance at the summary of this data set. So it'll be summary of air passengers. So we see that the minimum number of passengers for any month was 104. The maximum number of passengers for any month was 622. And the mean number of passengers is around 280. Okay. Now let's also plot this. So it'll be plot of air passengers and this is what we get. So here time is mapped onto the x-axis and the number of passengers are mapped onto the y-axis. So what we see is the number of passengers increase with respect to time. Now we can also add some labels and color to this plot. So the color which I'll be giving this is pale green 4, right? So I've added color to this plot. Let me also add a title to this. So it'll be mean equals passengers versus time, right? So this is the plot after giving the color and the label. So this is the color which you get. This is pale green 4 and the label which I've given is passengers versus time. Okay. Now what I'll do is I'll also add a linear line on top of this plot. So AB line of, I'll use the LM function and the dependent variable would be air passengers and the independent variable would be time of air passengers. So we have also mapped a linear line on top of this. So this linear line is nothing but the mean, guys, right? So the inference which you can draw from this is as the time increases, the mean also increases. Or in other words, the mean is a function of the time variable. But what happens is if the mean is a function of time, then this time series data is not stationary. So this is one problem. The another problem with this is the variance is also not equal. So if you take these two peaks over here, so the distance from this peak to the mean line and the distance from this peak to the mean line is different. Again, if we take, let's say, these two peaks, the distance from this peak to the mean line and the distance from this peak to the mean line is again different. So the two major problems are variance is not equal and the mean is also not constant. And that is why this air passengers time series data is not stationary. Okay, so now we'll go ahead and have a glance at the decomposition plot. So I'll type plot of decompose of air passengers and we get the decomposition plot. So this is the original graph and this is the trend line which we get. So we see that there is a general upward trend and this is the seasonal pattern and this is the random pattern. Now we'll also have a glance at the cyclical pattern, and to get the cyclical pattern we'd have to build the box plot. So I'll be box plot and I'll be giving the air passengers onto the y-axis and I'll be mapping cycle of air passengers onto the x-axis. Right, so this is the cyclical pattern, guys. So if we have a look at this graph closely, what we see is most of the traffic comes during the 7th and 8th months, that is during July and August, and the minimum traffic comes during 2nd and the 11th month, that is February and November, right? So again, I'm restating it, guys. Most of the traffic which we get is during 7th and 8th month, or in other words July and August, and the minimum traffic which we get is during February and November. So this is the cyclical pattern which we obtain. Okay, guys. So now, as I've already told you, this air passengers data is not stationary. So to make it stationary, we need to do two things. First, we need to make the variance to be equal, and second, we need to make the mean to be constant. So we'll start off with the first task. So we'll go ahead and make the variance to be equal. And to do that, we would have to use the logarithmic function. So let me actually plot the original graph first. So it'll be plot of air passengers. And we see here that the variance is not equal. Now, to make the variance to be equal, all I need to do is use the log function. So plot of log of air passengers. And this is what we get after using the logarithmic function. So this is the original trend line. And after applying the logarithmic function, this is what we get. Now let's also add the linear line on top of this. AB line, let me use the LM function. And this time the independent variable would be log of air passengers, and the dependent variable would be time of log of air passengers, right? So we've mapped this linear line on top of this. So this time what we see is the variance is equal. So the distance from this peak to the mean line and the distance from this peak to the mean line is equal. Again, if you have a look at these two peaks, the distance from this peak to the mean line and the distance from this peak to the mean line is equal. So guys, we have used a logarithmic function to make the variance to be equal. Okay. So now we'll also go ahead and make the mean to be constant. And to make the mean to be constant, we have to use the differentiation function. So let's do that. It'll be plot of def of log of air passengers, right? So log of air passengers gives us a trend line where variance is equal, and applying the differentiation function on top of this gives us a trend line where the mean is also constant, right? So guys, this is the graph where the mean is constant and the variance is equal. Now again, I'll plot the AB line on top of this. So it'll be AB line, LM, and this time it'll be def of log of air passengers, and the independent variable would be time of def of log of air passengers, right? So you have also mapped the mean line on top of this. You see that the mean is horizontal, or in other words, the mean is constant and also the variance is equal. So you have successfully converted the non-stationary data into stationary data. And that is why we can go ahead and build the ARIMA model on top of this. So before we go ahead and build the ARIMA model, let's understand it properly. So it's ARIMA. So over here, AR stands for autoregression, I stands for integration, and MA stands for moving averages. And AR is denoted with P, I is denoted with D, and MA is denoted with Q. Now to find out the values of P and Q, we can use the ACF and the PACF functions. So I'll type ACF and let me give in the original data set first. So it'll be ACF of air passengers. So guys, actually keep this graph in mind. Now what I'll do is, inside ACF, I'll give in the modified plot, which would be def of log of air passengers, right? So this is the modified ACF graph. So over here we see that there are no inverted lines, and over here we see that there are some inverted lines. Now to get the Q value, it will be that line which comes just before the first inverted line. I am repeating it, guys. The Q would be that line which comes just before the first inverted line. So over here the numbering starts from 0. So this would be the 0th line, this would be the first line, and this would be the second line. And since this is the first inverted line, the value of Q would be 1. So 0, 1, 2, and this is the value of Q. Okay, so let me give in the value of Q, which would be 1. Okay, now similarly, to get the value of P, we need to use the PACF function. So PACF stands for partial autocorrelation function, right? So again, it's the same case. To get the value of P, it'll be that first line which comes just before the first inverted line. So this is the 0th line, this is the first line. And since this is the 0th line, value of P would be 0. Okay. So we have found out the value of P and the value of Q. Now the value of D is just the number of times we differentiate the data set to make the mean to be constant. And since we differentiate the data set only once, the value of D would be 1. So we have successfully got the value of P, D, and Q. So the value of P is 0, the value of D is 1, and the value of Q is also 1. Okay. Since we've got the value of P, D, and Q, we can go ahead and build the ARIMA model. So I'll type in ARIMA over here, and inside this I will give in log of air passengers. After this I'll give in the values of P, T and Q. So it'll be 0, 1, 1. You guys must be wondering, why haven't I differentiated this? That is because I'm already giving the value of D to be 1 over here, right? And that is why I'm not differentiating this. Okay, so I've given the data set. I have also given the values of P, D and Q. Now I'll also given the seasonal parameters. So seasonal equals list, order equals C of 0, 1, 0, and after this I will also given the period, and since there are 12 months and 1 year, period would be equal to 12, and I will store this in, let's say, mod time. Right guys, so we have successfully built the ARIMA model. Now it's time to predict the values. So I'll use the predict function, and the first parameter would be the model which you've just built. So predict of mod time, and after this the next parameter would be the number of months, the number of years for which we'd want the prediction, and I'd want the prediction for the next 10 years. So it'll be 10 into 12, and I will store this in, let's say, pred time. Okay, so let me print this. So it'll be pred time. So guys, now what you need to keep in mind is all of these values are logarithmic values, right? So that is why we get values like 1.37, 1.61, 1.77. So we need to raise these values to the power of e. So the e value is 2.718, and I'll raise these predicted values to the power of e. So it'll be 2.718 to the power of pred time dollar pred. Okay, right, so I will store this back in pred time, and this time let me print it again, pred time. So guys, these are the predicted values. So we get predicted values from 1961 to 1970. So let's have a look at this entry. So the number of passengers for March 1966 would be 653. Similarly, the number of passengers for August 1970 would be 1271. And similarly, the number of passengers for November 1967 would be 655. Again, if we have a look at this, so the number of passengers for May 1970 would be 990. So guys, we have successfully forecasted values for the next 10 years. Now also we'll go ahead and make a plot of the actual values and the predicted values. So it'll be ts.plot, and let me give in the actual values which are stored in air passengers. Let me give in the predicted values which are stored in pred time. And since I've used a logarithmic function, so it'll be log equals y. Now I'll use the LTY parameter to represent all of the actual values with solid lines, and to represent all of the predicted values with dotted lines. So it'll be LTY equals C of 1, 3. Right guys? So guys, these are the actual values and these are the predicted values. So we have actual values from 1950 to 1960, and then we forecasted values for the next 10 years. Right? Okay. So now I'll also give a color to this. So it'll be COL equals pale green 4. Yep, so I've changed the color. Now also I'll give a title to this. So the title which I'll be giving is forecasted values. Right guys, so this is the final plot, right? So I've changed the color and I've also given a title to this. So guys, this is how we can work with the ARIMA model and forecast new values.
Now, if this session was useful to you guys, please like this video and also comment down any queries that you have in regards to this particular video. So thanks a lot for listening to me guys. Have a great day ahead and goodbye.